Welcome, everyone. I'm David Hansen, and as a UC Santa Cruz Alumni Council member, I'd like to welcome you to our monthly speaker series, Slugs and Steins, Lectures from UC Santa Cruz. For those of you who are new, our Slugs and Steins series engages a UC Santa Cruz faculty member in a discussion with you, the local community of the Silicon Valley, and our extended community online, with the goal of making us all Renaissance women and men. We want it to feel like you're at UC Santa Cruz sitting in class, but with drinks. Mike, another volunteer organizer, is with me tonight. We're both alumni and spend our days in entrepreneurial companies, Silicon Valley style. We miss seeing everyone in person. To try and capturing that in-person feel after tonight's talk, we'll open up an optional Zoom room for virtual networking and discussion. There will be a link in the chat and on screen at the end of the event. Please use those Zoom meeting credentials to join us in the networking space to chat about the talk and about UCSC. Our professor, in fact, will join us. Today is Indigenous Peoples Day. And in its honor, we'd like to start our session with a land acknowledgement, which recognizes the history and presence of Indigenous peoples of Santa Cruz and their enduring relationship to their traditional homelands. It reminds us that the lands that we appreciate now have been loved for thousands of years. The land on which we gather is the unceded territory of the Awaswas Yupi tribe. The Ama Mutsun tribal band, comprised of the descendants of indigenous people taken to missions Santa Cruz and San Juan Bautista during Spanish colonialization of the Central Coast, is today working hard to restore traditional stewardship practices on these lands and heal from historical trauma. Tonight, we're excited to raise a virtual Stein with a modern explorer, Dr. Doug Lin, professor in astronomy and astrophysics. Professor Lin has been honored as Guggenheim Fellow, von Humboldt Fellow, and Sackler Fellow. He's a recipient of the Otto Schmidt Medal, a member of the American Academy of Arts and Sciences, and has been director of the Kavli Institute for Astronomy and Physics. He's authored 262 refereed journal articles that have generated over 22,000 citations. And he's taught in universities in 7 countries, from Switzerland to China. In China, he went a step further, serving as founding director of the Kavli Institute for Astronomy and Astrophysics at Peking University. Now, impressively, he even has his own asteroid that will be circling about for a long, long time after we pass. The number 25133, Doug Lin. We'll take your questions via Zoom Q&A box. You don't need to wait to submit them. Type them in at any time. If you see someone else's question you like, you can upvote it and we'll ask it sooner. Mike and I will be reading the questions. The talk is being recorded. In a few days, you'll be able to find it on the UC Santa Cruz Arts and Lectures YouTube channel. We'll post the link in our social media channels and follow-up emails. Okay, so does everyone have their Stein? Hold it up. Great. I've got your slug, Professor Doug Lin.
Thank you very much. Let me say, first of all, I am really, really delighted to be here. I have been in UC Santa Cruz since 1979. And it is my home, and I really appreciate all the years being sharing this intellectual environment with students and colleagues. So some of the issues, scientific issue I describe is a result of that stimulating intellectual interaction. Okay, so let me start by sharing my screen and going to launch my PPT. Let's see if this works. Bear with me for a second, because it's a very big file. Can you see my file? Can you see my screen? Can you hear me?
Not yet, Professor.
We can
hear
hear
you.
you.
Okay.
We cannot see your screen yet.
You cannot see my, oh yes, I have to type share. Yes, that helps. Can you see my screen now?
Yes,
Perfect.
we're good now.
Okay. So I'm going to talk about 3 subjects which are as diverse, far apart as you can imagine. From the title itself, it tells you from the emergence of planets to the destiny of black holes. So the question is, what do they have in common? And how is it that we can provide a link between these type of processes? Okay, let me move to the next slide. So if you sit on, when I sit on the airplane, that was long ago, when my next door neighbor asks me, what do? I tell them that I work in astronomy. And the 3 most common or most frequently asked questions I encounter with is, are we alone in the universe? What's inside a black hole? What's before the Big Bang? These are incredibly sophisticated questions. In fact, we have just put together a poll and to ask you one of these questions. The first question, are we alone in the universe? And so this question has been, let me move on to the next slide, has stimulated great philosophers throughout the ages. In fact, around the time of the Greek and the Roman Empire as they emerged, and there were philosophers which were more important than the conquerors because they left behind deep thoughts. These thoughts includes a note from Epicurus to one of his colleagues, and in which he mentioned that there are infinite worlds, both like and unlike this world of ours. Almost exactly at the same time, there was a Chinese philosopher and a poet who posed almost exactly the same question as he raised the issue to the sky. He asked the sky, who is there to ask whether there is a beginning or there is an end, and whether there are other worlds like that of ours. So these are philosophical questions, and as my audience had generally expressed, that 90% of you, 93% of you actually feel there may indeed be life beyond Earth. But that is a philosophical question. That question really constitutes to what you think. The difference between philosophy and science is that science actually needs proof. And so that's the nature of the second question. Is there proof of life beyond Earth. Well, they're just starting to get some glimpse of proofs, but none of them are yet definitive. But that is, in fact, a reflection of your answer. 70% of you said there is no proof yet. And 27% indicated yes. And I think, in fact, we're on the verge of being able to answer some of these questions. So how did that come about? You may have heard the news last week, the announcement about the Nobel Prize award in physics. So what I'm going to talk about today actually is really the content of the Nobel Prize award for the last 3 out of 4 years. 3 out of the last 4 years. They were awarded to, in each case, to 3 colleagues, either for discovering planets beyond the boundary of the solar system, or about black holes in the center of our own Milky Way, or about black holes at very distant heart of the universe. So, and these are milestone scientific discoveries. And they are driven and stimulated by this quest to address the very issue, the philosophical issue that we have been posing. As much as for whether there's life else out there, the concept of black hole was also first raised by our imagination, by our philosophy, by our scientific derivation. But it wasn't until recently that we see very clear evidence of the existence of black hole and how they may influence the region around them. So what I wanted to convey to you through these first few slides is a difference between philosophy and science, but yet commonality between them. We need inspiration, we need a concept, and that concept, it drives our curiosity to explore the universe, and but that concept need to be verified with science, and we need to establish the proof of our claim. As Carl Sagan said, that extraordinary claims needs extraordinary proofs. So let me move on to indicate what our research effort has led us to discover so far. We first start with our neighbors. We look at Venus, we look at Mars, we look at Titan, we look at Titan is a moon around Saturn, and we look at Europa, which is a moon around Jupiter. And we try to look for evidence of life. We don't see yet any microbes or dinosaurs. We don't see dinosaurs running around in the horizon, nor even live microbes on the surface of any of these planets. We do see some circumstantial evidence that conditions suitable for life may exist. For example, there could be a vast amount of liquid water beneath the surface of Mars, as there are geysers spewing out water from the interior of Europa. Just a few weeks ago, you have also heard about the discovery detection of phosphine on Venus, which is yet another sign of leftover gas that's probably can only be produced by live species. But all of these claims are yet being examined very closely. And if we want to make that statement that there is an indicator of life, and we need to check all of the potential flaws in that argument. While we're concentrating on our own solar neighborhood, the biggest breakthrough occurred around 25 years ago. And when we started to look out beyond the solar system, we use various methods, try to look for planets around other stars. We try to directly image a planet around the star. The only problem is that these planets' brightness is very low compared to that of their star. So when you put a planet next to the star, you can hardly see it. It's like putting a firefly next to a searchlight. Nonetheless, a few planets have been discovered through this type of search. The first planet was discovered through the so-called radial velocity surveys. And that radial velocity survey is by detecting the spectra of the host star and see how it may change from time to time due to its own motion as a planet goes around it. So this effect of Doppler velocity is equivalent to the much dreaded speed checkers on Highway 17 when you are about to get a ticket and they measure your speed. So if a planet goes around their host star and the host star has a little bit of recoil and goes back and forth slightly, and just like two partners dancing with each other. And that has led to the discovery of the first planet in Switzerland. And then subsequently, UC played a major role in finding many more planets through this method. The third method is on the lower left, and this is called the transient method. Basically, what it is when the planet goes in front of the star, it actually blocks out a little bit of the light from the star, so it makes it a little bit dimmer. And the only problem is that the planet usually are very small compared to the star. And when this happens, the amount of light you dim by is less than a fraction of a percent. So you need very precise measurement of the brightness of the star. And this has been most effectively done by spacecraft. One particularly productive spacecraft is called the Kepler spacecraft, which was actually headquartered in NASA Ames. The fourth method is that when a planet orbits around its host star, it bends the space-time a little bit, bends the space, it warps the space, as Einstein has predicted. So if you can actually follow the brightness of the star, and all of a sudden you see a little dimming and then brightening of the background star, then you know that that region may have been perturbed by the presence of a planet. And it acts like a lens, and this is called the micro-lensing effect. And this kind of detection is done around the globe. You need to have a network of telescopes to follow a large number of stars to see how they change. Over the course of the last 25 years, well over 4,000 planets has been discovered. When I was a student, the only planets that we knew was in the solar system. And the major breakthrough came in 1994, 95, and now we have over 4,000 planets already known, and many, many more will keep on coming. And as we conduct this search. This slide tells you the various methods that people have used which I just described in the previous slide, the many different methods, the different color represents how these discoveries were made. They were made by people around the world, and both in the US, especially in California, and in Europe and in Asia. So this is a global international effort as we make progress. So many of these systems, as we make these discoveries, we find that many of them are actually in multiple planetary systems. In other words, around the same star, you can actually see many, many planets. In some cases, even 7 planets around the same star has been discovered. You say, why is this a big deal? Why is that a surprise? Well, after all, our solar system has 9 planets, or 8 planets plus Pluto, as we know. But these are extraordinarily precise detections because the signals are relatively weak. So when we start to see families of planets, we can then start to build a theory how they were formed together. In fact, I have been working on this problem for the last 45 years. And in my lecture in 1982, which I give in UCLA, I use a cartoon to describe the process, how these planet formation could take place. Today, because we know so much more, we now work on much more sophisticated theories and try to understand all the competing process, how it came about to make these planets as we see them today. Starting from a disk, and the solar system, the concept of forming a disk and then form the planets is obvious. And that's because when you go out there on a clear night, you can see some planets. They all line up in some way. What that means is that these planets are all orbiting around the sun in the same plane. And we see many of the planets today, they also orbit around their host star in the same plane, although some of them may depart a little bit. So in this plane, the gas cools down, and then you have silicates, ice will condense out to form little grains, and then they collide to form bigger grains. It's like a snowball effect. They become bigger and bigger, and eventually they become sufficiently big, they can accrete gas, and they can start to pick up gas from their surrounding region, influence their surrounding region, and become gas giant planets such as Jupiter. Now, there are 2 major paradigm shifts. What does that mean, paradigm? That means our concept has made major change. One is that the very formation process of the planets can actually impact the environment they're formed in. On the left, it was a computer simulation that my student from 20 years ago, a graduate student who did the simulation and showing the presence of planets can actually excite spiral density waves in the disk where they're formed. And on the right, this is the concept which we have advanced, that because of that interaction, that these planets can actually start to change their orbit. They can migrate. So it is kind of like when we go into UCSC class and majority of the people were born outside Santa Cruz, they migrated to here. And so to you, that should not be a surprise. But for us who try to build models, we see the endpoint. We have a concept that these endpoints represents some relic information of their beginning. So if I find it here, they must have formed here. And so this concept of changing location is new. Now, what is really interesting is while we're developing the theories and try to explain planets beyond the solar system, there has also been a major advancement in trying to detect the region where stars are formed and planets are formed. And these are in gas clouds, but they produce infrared radiation. They cannot be seen with a visual light. So in the last 10 years or so, there have been a major instrument that was built on top of it's Elma. It's in the high desert near Chile, between the border of Chile and Atacama Desert. And the Atacama Desert, there is a plateau which is 5,000 meters wide. In this plateau, it's very dry. It's ideally set up for infrared observation. Several hundred of these radio telescopes are put up there. And so from these radio telescopes, we're starting to probe the image of the star-forming region, and we're finding disks, these protostellar disks, with structures in them, which may indicate the presence of emerging planets. So this has been a major advancement. It's an incredible sight. Since I was a student at that time, we don't know of any planets outside the solar system. We didn't know any of the evidence of disks around other stars, young stars or old stars. And but today we have all of this knowledge and we're making advancements. So this is a good point to pause for a few minutes, maybe address some questions.
Hi, everyone. This is Mike. I'm the other host with David. We're going to take a few questions right now, and I'll just remind you, you can ask your questions at any time down in the Q&A box. First question is from Stuart, from Stephen. This is back to the exoplanet discussion. How do you distinguish between transit and microlensing data?
Transit actually dims the light a little bit. And the duration is very short. It's minutes to hours. Whereas the microlensing, it lasts more than a day. And it actually brightens the light of the background star slightly because it tends to focus the presence, the gravity of the planet actually pulls the light from the surrounding region and focus it. And so you get a little brightening of the star.
Oh, interesting. David?
From Stuart, while it may be interesting to be discovering many exoplanets now, with all of them so far away, do we stand any chance of ever being able to visit any of the Goldilocks planets?
It's a very good question. In fact, we're starting to find planets around the nearest stars. And so nonetheless, astronomical distance is vast, and it takes light many years to get there, and let alone spacecraft. And so probably the best way to really look at these planets is through their light, through their property, observe them. But if you have to eventually travel to there, And perhaps a physical travel is not necessarily the best means. After all, I will talk about at the end that life is really, in many ways, composed of information which can be digitized. And are there ways that we can explore information from these faraway places and through at the speed of light rather than at the spacecraft's speed? And this may be an interesting concept for future generation to explore.
Thank you. Last question for now from Samuel. What is the role of computer simulations in advancing knowledge of these processes?
Very important role. And the reason for that is that we come up with some basic concepts. But planet formation is a very complex process that involves many different aspects of physics. It is just like if I want to know about your personality that is being influenced by many factors. So the only way to do it is if we put together a simulation and try to see how the different competing information, competing effects can dominate one over the other, and what is the most likely effect that will produce what we see. So computer simulation is enormously important. Okay, so maybe I can go to the next set. So I talked about these disks. I talked about this exciting discovery of all these disks, and that not only tell us about the origin of our planets. It turns out that this concept of disks would dates back to Laplace in the context of planets, but it also dates back 40 years earlier to another group of people who were looking at these very strange phenomena at the very edge of very vast distance away from us. And these are called quasars. They are the brightest beacon in the universe. They outshine the sun by a trillion. And they are almost look like a single point. And it was around that time, as you can see, 1963, when the first ones were discovered. And it didn't take very long before a theorist, who was also partially my advisor in Cambridge, Donald Lindenbell, came up with this idea that they were powered by infalling material onto the center of a massive black hole. And this material, when they go in, it forms a disk to produce enormous amount of light. And over the years, since that time, there have been many observations, many done by colleagues here in Santa Cruz and elsewhere in the UC system, try to examine these quasars or active galactic nuclei. It was a couple of years ago when people looked at one of them near and they see this so-called shadow of a black hole in the center of M87. And so, and we see that the evidence of these massive black hole is starting to emerge. And so this concept that how do you power it is that with a very central region, if there is a black hole, and when you fall into a black hole, light cannot come out. But if they have a little bit of what is called angular momentum, and they will spiral and spin together to form a disk, a little bit like your wash basin in your bathroom. When it goes down the drain, it forms a little whirlpool. And in different parts of that whirlpool, gas move at different speed, and so they rub against each other, produce enormous amount of heat in the form of radiation. We detect these by visual light and also by radio telescope. And from various sources, we can measure how fast they move. We can figure out how much material is falling into these black holes. One of the most exciting discovery was done in the last 30 years. And again, almost at the time when it was 1995, when after the Keck telescope was built, and using the Keck telescope and with a laser guide star, and we were able to get rid of all of the obscuration caused by turbulence in the atmosphere. So people can now measure the position of the star very precisely. There's a group in UCLA led by Andrea Getz, and who looked at this group of stars. And over the years, she noticed the position of the stars have changed, and they orbit around. There's some dark point in the center, which we refer to as Sagittarius A star. And by looking at how fast the orbit moves around, and we can actually figure out exactly the mass of this black hole. And there was also a campaign that was done in the Southern Hemisphere with European Southern Observatory by Reinhard Genzel's group and from Germany, although Reinhard also spent a small fraction of his time in Berkeley. So these are the two folks who won the Nobel Prize this year for the discovery of the black hole at the center of our Milky Way. I will talk more about these type of stars a little later at the third section of this talk. And but with these stars, with these disks, and one can develop some theory. And the idea of trying to understand how these stars may have formed in these disks and how they may have interacted with the disk and how they may have evolved. In the last few years, this is what I have been doing and trying to understand aspect of this. In fact, it's not just a few years, and we have been looking at this type of problem since the early 90s. So if you have a black hole in the center here, and then you have a disk around it, you have all these stars going around in the disk. Each time they go through the disk, they feel a little drag, and they can evolve into a larger and larger objects. So I want to impress you at this point that study of the Galactic Center, AGN, this type of phenomena, is very similar to study of planet formation. Because in the center of these disks, there are massive black holes whose mass is about 1 million times more massive than the star in the disk. In a protoplanetary disk, the mass of the central star is also about 1 million times that of the planets. The period of the planets ranges from days to centuries. The period of some of these stars ranges from years to millennia. And so they are very similar. And the size of the planets to their distance from the whole star is about 1 in 10,000, like the stars around active galactic nuclei. Even the disk around these objects, they have very similar analogs between the disk around active galactic nuclei versus around young stars. So what we need to do is to understand how these type of process, competing process, could operate under these vastly different yet similar environment. So this was a complex study, how a star that goes through this region may actually end up passing through the disk. While passing through the disk, how does an interaction, how does it slow down or lose a little bit of mass? And let me move this out of the way so I can actually get to it. How it may pass through the disk, and the star may lose a bit of its envelope. And over time, they gradually end up and in the disk in a manner that is very similar to the presence of young planets inside these protostellar disks. They even create environmental impact by opening up gaps and induce spiral density waves, and along the way, they may migrate. So what do they do in these disks? Inside these disks, that the only difference is that these stars will grow very fast, like planets grow, and they will evolve off their main sequence, produce supernova, generates huge amount of heavy elements like carbon, nitrogen, oxygen, or even iron, and they will produce these type of elements which are made of you and me, and they also produce black holes, neutron stars, and white dwarf. Very exotic. In this environment, and we can use this type of model to explain when we look at very high redshift, namely very distant quasars and active galactic nuclei. We see that they have a lot more of these heavy elements than in our neighborhood. So this may be the reason, and this may be the consequence of a evolution. So I will stop here for a second, and you can ask some more questions before I move on to the Galactic Center.
So we have one question from Stephen. Galaxies are often in disk, but not all. Does that mean that there are galaxy formation methods, different galaxy formation methods, maybe without massive black holes in some?
This is a very good question. And many galaxies are disk-like, many are almost like football in shape. And those are the outer region of the disk. At the very, very center, maybe less than 1,000th of those sizes, the very center is where the nucleus, where the black hole are found. We generally find black hole around almost every galaxy we care to look. And some of the black holes are larger, some of the black holes are smaller, but there is a general tendency, there's a link between their mass and the type of galaxy and the mass of the galaxy they're in. Galaxy formation is also very complex. How do they take up different shapes and how do they evolve? And we're gradually trying to understand them. And by understanding all these different pieces of the jigsaw puzzle, we're building a more and more comprehensive picture of what's going on.
Question from Dong Wook. How can we understand that strong energetic radiation, such as quasars, can be puke out of black holes, given that nothing, including light, cannot even come out of these heavy, massive black holes? Maybe say exit instead of puke?
Yes, okay, so this is also a very good question. Inside the concept of black hole as envisioned by many, including Einstein and Stephen Hawking, is that from the light from inside the black hole cannot escape. But the material that falls into the black hole on their way, and they have a lot of energy, a lot of kinetic energy, and they form these disks, they rub against each other. They're actually outside what is called the event horizon. Namely, they're outside the region and then where the light cannot escape. So there are very easily capable to be able to escape. It's a little bit like you're rafting on top of Niagara Falls, and the loud noise you heard of the rafter that is struggling is the one that's still on top of the fall, but not at the bottom of the fall. Once you get to the bottom, that is done. And but on your way down, there is an enormous amount of energy dissipation. That's what powers the electromagnetic radiation that we see. Okay, I'm going to move on to the next topic. We still have more questions and answers later. And so the next question is that all these little black holes are formed, and you accumulate over time, they gradually will build up, and they can accrete, and they can consume more gas, they can become more massive, a little bit like the planets inside the solar system. And these objects, as they accrete, and they start to capture each other, they tend to attract each other. And this little movie is running in time, and the vertical direction is their distance from the center. The size of these color spheres are really representing the mass of the little black holes. So they can actually capture each other, and they can grow, and they can exchange partners, and they gradually grow. Okay, and during this very process, you can form binaries and multiple systems. And when these binary and multiple systems get closer and closer together, the black hole gets closer and closer together, they may be able to coalesce. When they coalesce, they really perturb the space-time fabric near them. And now they're going to send out a wave, kind of like a seismic wave, except it is the whole space-time. It's not the electromagnetic light that we see. And these waves shake up the entire universe, and it sends out. But because they're so far away, it's very faint, and we can't detect it so easily. And for the last 20 or 30 years, again, there have been many dedicated scientists all around the world to build up these what's called gravitational wave detectors. And these detectors are designed to measure the absolute minute amount of change in the space-time, namely the distance between points which are separated by kilometers, and how they can shake a little bit as the wave propagates. So, and you can see that how these little black holes, when I say little, in the first case, it was a 29 solar mass black hole times the 29 solar mass means 29 times the mass of the sun, merged with something that is 36 times. When they merged, they shook the universe. But because we're so far away, that influence was not a big deal. Today, we know that there are many of these events have been detected. This is the first event was detected in 2015, and now we have dozens of these type of events. And we can detect mergers of black holes with very different masses, and they tell us a lot about physics under extreme condition. And when gravity is so enormous, and how they may perturb the space-time around them. Even their spin can cause the shape of space-time to get distorted a little bit. So when they eventually merge, and they can actually either escape or leave with a, or go somewhere else with very large speed. We can measure that spin, we can measure their mass, we can measure how fast they move. And eventually, some of them, as they merge, becomes bigger and bigger. They will start to perturb the disk in the way that we know the planets when Jupiter is formed, remember I talked about this paradigm shift, you can actually change the environment. You can get the environment to generate spiral density waves. You can cause migration. You can cause the migration of these intermediate mass black hole. The intermediate mass may be thousands times that of the sun in terms of mass, or even larger. And they eventually will get close to the massive black hole in the very center and merge with them. The current generation of gravitational wave detectors cannot detect those signals because their frequency is not quite correct. But the next generation of gravitational wave detectors will be launched in space, and we can then have several of these satellites. We can measure as the wave, gravitational wave of large black holes merge into the supermassive black holes as they propagate, and we can measure them. And we can measure them to a distance that is greater than 1 billion light years and beyond. Now, but most of these waves are going to be in the form of gravitational effect, and it's a space-time, you don't see the light. But they may influence the surrounding region a little bit to produce light. So there is also a campaign that we're trying to do, is to look at the electromagnetic counterpart of these events. That requires participation all around the globe. In fact, some of my colleagues at UCSC have been heavily involved in this campaign, try to find the electromagnetic counterpart of these gravitational wave events. Now let's return back to the Galactic Center, because if these effects happened out there at billions of light year away, and they're too far for us to look very closely. What about the Galactic Center? Didn't I tell you earlier already that a massive black hole is found there? What can we see there? If you look into the visual light, the light that your eyes are sensitive, here is what you see in the Galactic Center. Nothing really spectacular. But if you look into the infrared, there's a concentration of young stars near the very center region. And these stars all are about 4 to 6 million years old. And it seems that 4 to 6 million years ago, something has happened near here that caused these young stars to form. And we can detect that event because we see, by looking above the galaxy, we look into these regions. In the X-ray, we see there's a bubble, as if though something has happened near the center of the galaxy, that this bubble has popped out, and that bubble occurred about 4 to 6 million years ago. So from that, we can infer what is present there. Once we know that may have happened in the Galactic Center, can we see some evidence what's going on? We see these young stars, they have very complicated orbits, and they move around in some way. And one important question is, can they get the kind of orbit that we tend to see if they are formed in a disk? They should all be circular. Why are they so chaotic, so eccentric? And so could they be perturbed by something else? And indeed, there are candidates around here, and which is what is called the intermediate mass black hole, which may be only 10,000 times more massive than the sun, and a mere baby compared to the central black hole. So now, if that is the case, we have an incredible analogy with the solar system again. So then this object will be about 0.2% the mass of the central black hole. Jupiter is about 0.1% the mass of the sun. So the evolution of Jupiter in the early days help us to understand the evolution of these young stars in this current configuration. And we're making a lot of progress in here. Another very interesting effect is that if you can get them to become eccentric, they may go very close to the central black hole. If they come very close to the central black hole, they can actually get a slingshotted out to move at very high speed that is large compared to 1,000 kilometers per second. But before they go out there, and some of them, when they come too close, they may get totally disrupted. They may get torn apart. And there are some indication of some events around center of galaxies that massive black holes are tearing stars apart when they come too close. Once again, we can draw analogy with something in the solar system. Just 3 years ago, there had been a serendipitous discovery of an interstellar asteroid that came into this inner part of the solar system and went out again. Everybody is mystified to its origin. One of the theory that we have been producing is that this may be produced by something just like what you find in the center of galaxies, but around another star, when an asteroid moved towards the center of that star, and it got torn apart and broke into pieces, and it formed into a cigar shape, and a lot of it, the remnants gets thrown out, and as they get thrown out, they get picked up by the solar system again. I have only 2 or 3 more slides left, so I can go. So this object will come close to the solar system, and we just happen to pick it up with the existing telescope, which is not so powerful. But in a few years to come, we will have a most powerful telescope called the Vera Rubin telescope, which will take a picture snapshot over 5 years, every 4 days, everywhere in the universe. So we can play the universe as a movie, and we can pick up these objects. These are the interstellar visitors. So these interstellar visitors will be studied and carefully to see whether there's a possibility that we may have been bombarded by some of these. That raises the possibility that if there are life elsewhere, could this life be transported from a stellar system, one place to another place? This is the so-called concept of panspermia. And it is an idea, and that is just a speculation at this point. And so to detect the possible signature of life around all the nearby planets, and we will soon have an incredible space telescope called the James Webb Space Telescope that will enable us to look into the infrared, pick up signals of possible life. So on the last note, I want to say, we come back to a philosophical point. We come back to the point that life on Earth started almost as soon as it was possible. And the first sign of life emerged only a few 100 million years after the Earth was formed. Did that form spontaneously on Earth, or could it there been transportations of life, one form or another, not necessarily physical, but biological through digital transmission? And so the question now is really a philosophical one, and ends up on the node of uncertainty, namely anthropic principle. What we observe is this extraordinary piece of puzzle. And the very fact that we can raise these questions may already tell you that the condition of the universe had evolved to this point to enable us to raise these questions. So the link of our destiny and our existence may be intimately connected. On that speculation, I thank you for listening to me.
Wow, and I thank you. I must say I'm amazed. We do have questions from Samuel. What is the role of dark matter in galaxy formation and in stellar system formation?
The role of dark matter is very important. And again, this is something that we only come to the realization over the last 40 or 50 years. And we see around the outskirt of galaxies, there are a lot of forces that's pulling us together, but we don't see the light from it. So that's why it's called dark matter. It's a matter that provides the gravity, but not provides the light. And it is thought that this type of process this material has contributed to the force that pulled ordinary matter together. Ordinary matter, when we say ordinary or dark matter, we really are very self-centered. When we say ordinary, we're referring to matter that's like what composes of us. But what matter composes of us is only a tiny percentage, a few percent of all of the mass you can account for in the universe. And the dark matter is at least a few times larger than that. And that material provided the gravity that pulled the first building block of galaxy together and still dominates the structure of galaxies further out. Exactly what it is, we don't yet know. It could be in the form of small particles. It could be in the form of some dark objects, and we don't know yet.
We have a combined question from Justin and Matt. How fast do gravitational waves caused by merging black holes travel? And what would happen if a merger happened in our vicinity?
Well, it travels at the speed of light because it's not of mass or not of photons. It travels at the speed of light. The whole space-time fabric would change a little bit. It is not that dramatic if it happens in our neighborhood. It's just that the space-time gets changed a little bit. It's like you're sitting on the elastic band. The band moves back and forth. You don't get completely baked, or it's not like I'd rather to be on the moving elastic band than to be next to some big fire, especially the one that burned down our neighborhood. And so it's not that dramatic, but it really helped us to, for the whole universe, it does matter in the sense of it changes this, the shape of the space-time. So it's a collective on a much larger scale.
So we have a question from Asha and their 10-year-old son. Can a black hole stop working, or do they work forever? And can two black holes coexist in one galaxy?
I'm really glad this question came from our young audience. That is actually a really very deep question. And I remember because I have been, I was a graduate student in Cambridge at the time, and I was a graduate student. My next door neighbor was Stephen Hawking. He asked this very question, that can black hole actually evaporate? Can it evaporate? Can it, would it be there forever? So, and his most famous contribution is, black hole evaporation. And of course, these are very, very small black holes, and then the efficiency would be high. But the concept was there. So, and this is one of the three questions I posed in the beginning. What is inside a black hole? And that's certainly beyond our horizon, both in terms of physical reaches and concept at this point, and exactly how we can communicate between this region where even the light does not have enough speed to escape. And can the fabric of space-time be connected in some way that information can still propagate? So this is a very deep question, and I hope our young audience may be able to tell me in 20 or 30 years' time, and try to explore that possibility.
Oh, I think Samuel, or they also asked, can two black holes coexist in one galaxy? Second part of Marcia's
Well,
question.
we think there are many black holes in our galaxy. So that even in these, there are many other, inside the Milky Way, we think there are probably, it's hard to estimate. It's probably about a few million black holes. But on these disks, which I talked about, in typical active galactic nuclei disk, you may have up to 10,000 black holes that is contained inside this disk. So, and that enhances the possibility of binary formation and coalescence. And that's why we see them in the way that we do. So, and in this kind of environment, I mean, black holes are in these environments are a little bit like human beings. You see, when we were born, we are relatively small. And by our 20s, we grow into 10 times more mass than before. When we were born, most of us are singles. And when we're in our 20s, we find partners and form these equivalent of binary black holes. And this kind of evolution is actually easy to link how evolution could take place in these environments. And the density of the black hole does matter, and how many you have in this neighborhood that actually determines the probability of being able to detect them. So once we have these theory, we need to go to try to figure out what are the observable properties, and that's our next step.
So next question from Antonio. What are the conditions required for a black hole to form? Is it possible to date the formation of each one, or is there more information that needs to be gathered?
There's a lot more information need to be gathered, and different size black holes form maybe very differently. For example, if our sun were to run out of nuclear fuel, it would not form a black hole. It would form a white dwarf in the middle, and with its envelope expand. But if there is a star that is 20, 30 times more massive than the sun, at the end of its evolution, and the central part of that, star will collapse and pull together and form a black hole. But the black hole I have been talking about at the center of active galactic nuclei, there are millions to 100 million times more massive than the sun. That is a major puzzle on how they came about so quickly, so early in the evolution of the universe. In the first billion years, we have already witnessed when we go out to very, very far distance, and that we're looking back in time that it's the first billion years of the universe, there are already black holes with mass about a billion times that of the sun. And that is a real challenging puzzle. So what I am working on is in the hope of trying to understand these puzzles, not only to understand how the gravitational waves are formed, how we can utilize the gravitational wave to probe the very early universe and try to see how these massive black holes form. And in the same way as when we were studying planets and try to understand the moment that the planets are formed based on what we know the planets are mature planets properties are, and try to figure out how we can go forward. And this quest to dig deeper is with us. So even though I am now an emeritus professor, I actually work more intensely than ever with people around Europe, Asia, and the US. And pandemic has been actually very easy for me to handle because I'm at home all the time and I'm on Zoom all the time throughout the day and working on these problems.
That's a good point to segue. I'm going to take the facilitator's right to ask you a question about China. Now, you've been a scientist big time both here and in China. Can you share insights from the difference? How were you treated as a scientist in the two countries? And what do you see as the prospects for science in both lands?
I think this is precisely what the very question that I asked myself when I was invited by the Kavli Foundation to start an institute in China. And now Fred Kavli is a philanthropist and based in Santa Barbara. And he was a Norwegian and with incredible vision. And he wants to develop 3 areas of basic science for the benefit of humanity. And these 3 areas are in nanoscience and also in neuroscience. And he wants to study the biggest and the most complex and also the most challenging problems. So, and initially he formed several institutes around the US, and then he expanded globally. And he was interested in China. And it was a time for me, it was a really good opportunity, precisely because this was in 2007. And I feel that with knowing many people in many parts of the world, and I really shared the vision of Fred Kavli and wanted to make a difference. And because I know there are many, many talented students there, and they are all looking for opportunity to embrace modern science. And at the same time, at the time, China was not as affluent as today, and so the opportunity was limited. So I went to China, and I stayed also at UCSC and provided a bridge between the two shores of the Pacific. And my objective was try to see whether we can engage these young people in terms of engage in science, especially in areas of astrophysics, in these emerging areas such as exoplanets and gravitational waves. And so it was a very rewarding experience for me. And because I was invited to the top university in China, Peking University, and at a later stage, I decided that I would only do this job for 1 term, partially because I'm also really enjoy what I do here. And so I stayed for 5 years and got it launched. And then I returned back to UC Santa Cruz. But I maintained my intellectual connection with the students, with the young colleagues there. Many of my ex-students have gone on to graduate school in the US, leading places in the US and Europe. And just this last summer, in July, I was very moved by something like 2,000 people came to Iceland to celebrate my birthday, and there were a lot of people from all different areas of the globe. We were, we were attracted by similar problems, and I feel I truly believe that fundamental science has no national border and no subject divide. And if you really are a global thinker, and science belongs to humanity, and there is no division between chemistry, physics, biology, and astronomy, and one need to leave no stone unturned when you try to get to the bottom of subtle and deep problems. But at the same time, you must not lose the big picture. And I feel that during this time, as I worked with students across different culture, and I was able to help me to focus on these points. I hope that addressed some of the issues that you have asked.
Indeed. Mike, I thought it was your turn. Are you taking over?
So next question from, oh, I'm having trouble finding it. I'm sorry. It's scrolled off the screen. If you have it, why don't you read it?
Yes, from Alexandra, should there be a dramatic redshift in energy emitted just before the event horizon of a black hole?
Well, if you can see the light of the material that is falling into the black hole, what you said is absolutely correct. And because it takes, the time gets stretched out, and space gets stretched out. So the wavelengths of the light that's emitted as you fall into the black hole gets changed. It gets longer and longer, and that's what you mean by redshift. Another way to think about it is, this is just an analogy, but suppose you are falling into the black hole with your feet point closer to the black hole. Okay, your head is further away. Then the feet being closer to the black hole actually feels stronger pull than the head. So then you get, the feet gets pulled fast, more strongly than the head, and you get more and more elongated. So you become longer and longer, and think of that as a photon. And so you can actually change this aspect, and these type of effects are important to understand the spectra from a black hole. That's why in the beginning of my slides, I showed you the shadow of black hole, and around the black hole in M87, and you see there is a little glow right near there. Those are not the light that went just near the black hole, but it was behind the black hole, and the light gets focused and then it gets distorted. And so to understand those type of image, we really need to understand how light and space and time gets influenced in the presence of strong gravity by black hole.
And we have some similar questions from Pearl and Peter. Will the Earth, or maybe someday the entire universe, end up in black holes?
Well, let me address the second issue first. Okay, I think some feel that the universe is actually inside a black hole. When you get into bigger and bigger black hole, it doesn't mean that the density gets infinite in this, it may get infinite in the very center, but it just means that there's a region of space-time that you cannot escape from. So if the universe is in such a sphere, we call it the closed universe. So the universe, you cannot escape from that. Then in that sense, the universe is a gigantic black hole. But today we think the universe is not closed. It's more like it's open. And so what are the evidence? So then what makes the universe close or open is whether there's enough gravity to pull us back that we can never escape. So how do you measure the gravity of the universe? That's very hard. But what you can do is that gravity actually slows you down. You know, when I jump up, the gravity slows my motion up and then eventually pulls me down, okay? So if I can observe the universe causing me to change my speed, then I know something about how much gravity there is in the universe. So now how do I do that? That happens on time scale of billions of years. So what I can do is to look at more and more distant galaxies. When I look at more and more distant galaxies, I'm actually looking at earlier and earlier time. So as if though I'm playing a movie of the universe, if the further I look and the earlier time I'm looking into. And then I look at how they are moving apart from us, whether they're accelerating or decelerating, and then therefore we can work out the state of the universe. And that was done a few years ago, I mean, a couple of decades ago, and that also won the Nobel Prize. So you have posed a very important fundamental question. What about the Earth? Can the Earth get inside the black hole? Now, the mass is much lower than that of the universe. To get the Earth inside a black hole event horizon, you need much, much higher density, much higher than nuclear density, and you really have to squeeze it, okay? And that's very difficult to do. But there are these concepts. Hawking was one of them that postulated that in the very early universe, there may be, when the universe was highly dense, so dense that that even nucleus are touching each other, and you didn't have the physics you have today. At that time, maybe there were tiny, small black holes that could have formed. And they would have very interesting properties. But we have no evidence of any of that at this point. All we know is that this concept exists, and maybe one day, you know, we should be looking for some implications that that this kind of phenomena does exist.
Okay, Parol, I think I detect no reason for panic yet. We have one final question. This from Emiliano. What findings and implications do we gather from the macro level observations of the universe that we are using to apply to our micro level struggles with our planet and humanity?
Very profound question. Okay, so this, I think there's a lot to learn from the universe around us. You see, in a way that when I never really understood when people in my youthful days, and they said, you got to study history, because if you don't know history, you're condemned to repeat it. And I think that is really the case. And you should know about your environment in the universe, because that if you don't understand the universe and you don't understand what's going out there, and you are likely to make mistakes that's irreversible. We do know things like atmospheric conditions in Venus. We know changes happen in Mars. And we know that the Earth has a Goldilocks, environment, and that's very sensitive. And the study of the global universe help us to understand many aspects of microphysics nearby. And when we get more information, it can only be good, not bad, because I rather have an educated guess before I go into a stock market than just randomly go in there and to gamble. And so knowing the world around you is important. And I feel knowing that a little bit of the glimpse of the universe helped me to have a better perspective as we see. So I remind you on that ending note that the anthropic principle, Brendan Carter had raised, and has social philosophical implication as well as scientific implications. Thank you.
Well, thank you, Doug. We do still have a few questions. I'm sorry we can't get to them all, but we're just about out of time. You can feel free to keep typing questions in the Q&A box, and maybe Doug will give you some brief answers by text if he has some time. But unfortunately, we have to wrap up. And so I'd like to thank everybody for coming tonight, and thank you, Doug, for joining us this evening. This talk has been recorded, and it will be available on the UC Santa Cruz Arts and Lectures YouTube channel in a few days, so check back. As soon as we wrap up here, we invite you to join us in the Zoom meeting room to chat with us, with Professor Lin, and with other participants. Information has been shared in the chat box at the bottom. We'll put it up on screen as we close. So I hope to see you there. Another big round of thanks to the staff of the Alumni and Special Events Office who set up this online forum for us. Thank you very much, Cara, Diana, Paulina, and Kristen. Our next event is Monday, November 9th, featuring Professor Silvana M. Falcone. She is the founder of UC Santa Cruz's Human Rights Investigations Lab for the Americas. And her talk will be on the evolving practice of human rights accountability, New Terrain for Justice. She will explain how human rights accountability has shifted in the digital realm and describe ways in which a new generation of human rights activists are needed with critical digital literacy skills in search for the truth. In the meantime, some other exciting online talks from UCSC are coming up. Tomorrow, October 13th, the UC Santa Cruz Institute of Arts and Sciences invites you to join us for a special online laser talk featuring David Stork, Ari Friedlander, and Yolanda Harris. Discussions will range from computer vision and pixel painting to immersive sound and video work exploring the underwater world. It should be fascinating. October 22nd, Professor Holger Schmidt will headline a new crawl lecture, Hunting for Infection, One Molecule at a Time. This is about optofluidic hardware capable of diagnosing viruses quickly and inexpensively. You can check for these events and others at calendar.ucsc.edu. This is your last chance to sign up now for our virtual networking and discussion room to follow. The link for this again is in the chat box. On behalf of UC Santa Cruz Alumni Association, thank you for joining us, and please come back on November 9th for our next virtual event. Bye, I'll see you in the chat room.